All right, welcome back, everybody. Gonna move on to the next part of our chess engine. In this video, I'm going to implement the algorithm called Nega Max, which is kind of a combination. It's just another way of implementing the MinMax a little bit cleaner. And then also we're going to add in alpha beta pruning. Now, some of you guys have left some comments like, yeah, it's really slow. It's really slow. And there's two reasons for that. One, the MinMax algorithm doesn't make any efficiencies. That's why we're going to add in alpha beta pruning. So one of the things like it is the MinMax is checking every single position, regardless of how it scores. What alpha beta pruning will allow us to do is basically to not visit branches that we know can't be any better than our best possible score already. So it allows us to prune or cut off basically branches of our game state tree that we don't need to visit. Since our opponent will play optimally, there's no point in visiting some move branches where we won't be able to get a higher score than what we've already found. Now, it's not going to give us as big of an improvement as we would like it because it also depends on our scoring algorithm. Our scoring algorithm right now is very, very basic, where it's only counting points, and that's it. It's only counting pieces on the board. It doesn't care anything about position. And if you've played chess, you know position is material is big, but you can be down material and still have a winning position. So we want to also start adding in positional things as well. I'm not going to get into that in this video because this is going to require us to change our engine itself. I think is the most efficient way of doing it. But we're going to start to consider things like which moves, or like how many moves are even available, right? Like if a bishop can move to like 10 different squares, that's generally better than a bishop that can only move to like one square and then is blocked by its own piece. Or similarly for like a queen or a rook. And then for like a knight, typically a knight that's near the center of the board that has more squares that it can control is a better knight than one that's on the outside of the board. And so we'll have our computer consider things like that as well. Pawns that protect each other, so pawn chains, we'll consider those as well. Again, that's going to be in my next video, so I'm not going to do that yet. So this, we are going to see some slight improvement in terms of speed, but we're still it's still going to be slow. And the reason is many of the board states are going to be equal to each other in terms of score, and so it has no way of ordering those things. And we'll talk other things that we can do in terms of efficiency. One of the things you can add in is like things called transposition tables. So for example, like if I make a move and then black responds with a move and then I make another move, that board position is the same as if I had switched my move orders, but black makes the same move, right? So we can wind up at the same position or transpositions of a position based on move order. And the score of those should still be the same. The score of that state of the board should be the same. So there's ways you can, keep track of those scores and things like that. I don't know if I'll get into any of those, but I can maybe point you in the direction if you want to try and implement those yourself. But again, that stuff's going to be focused more next video. So I want to start with this Nega Max algorithm here. So we had move MinMax, and we did this last video. We had if white to move all of this, and then otherwise if black to move all of this. And the idea was here we were trying to maximize the score, here we're trying to minimize the score. But you can see the pattern is very, very similar. There's just a slight difference here in terms of the comparison, in terms of the variable names. And so there should be a way that we can implement this a little bit better. And so that's what we're going to do in this next method here. So under find, it doesn't really matter where you put this, but I'm gonna do it under find move MinMax. I'm gonna create a function called find move Nega Max. So Nega Max is the name of the algorithm that combines MinMax. It's going to take a game state, it's going to take the valid moves, and it's also going to take a death. Very similar to what we did here. And it's also going to take this white to move, but instead of it being a Boolean variable here, it's going to actually be a negative or positive number, negative or positive 1, when we implement this thing in. So it's going to be 1 if it's white's turn to move, and negative 1 if it's not white's turn to move. So I think we'll be able to use a similar helper method as well. So I'm gonna rename this helper method in a little bit. We'll get to that. But let's write this method. So we also need it's not white to move because it's not a Boolean value. So we'll call this turn multiplier like we did before. I want to think of this as -1 or positive 1. That's the way this works. And that's going to tell us kind of which way we want to go, minimize or maximizing it. And the idea in the Nega Max is that we'll always be looking for a maximum, and then we'll just multiply it by -1 on black's turn. So basically the same thing here. Like we could think of this if we were doing the minimum. If I just negated it, then I'd be finding the maximum. So that's kind of the idea behind this. Okay, so it's going to, again, look very similar. We'll have our next move, just like we had before. We'll have our base case. So if depth is 0, then what we're going to do is we're going to return the turn multiplier, which is going to be -1 or 1, depending on whose turn it is, times the scoreboard of our game state. So we're going to call our score method. It's very similar to here, except that in this case, we didn't have that turn multiplier, because in MinMax, we were always looking at the board in terms of whose turn it was. Now we're just looking at the board as it is and then multiplying it by the turn multiplier. A little bit different. But the idea now is I'm only going to need one of these for loops, one of these if statements here. I don't really need to check whose turn it is because the algorithm will work in both cases. Let me zoom in a little bit. I think it's a little small. Sorry about that. Okay, so we're gonna follow the same logic here. So let's look for our max score. So we'll set our max score equal to negative checkmate, basically the same thing we did here. We're basically gonna redo this with like slight differences here. So we're still going to go through each individual move. So for move, invalid moves, we're going to make each move. And we are going to undo each move. And at the end of method, we're going to return our max score. So in between making the move and undoing the move, we're then going to call next moves in order to get our next set of moves. We're going to call get valid moves. So let's see what our opponent can do. So get valid moves. And then we'll find our score. And our score here, this is the where the power of the Nega Max algorithm comes into play. It's this negative sign right here. This negative sign is really, really important because we're going to basically call this method again for our opponent, and whatever their best score is, then that is the worst score for us. So this negative square is this negative sign is very important. If it's blacks to move and they get a negative score from, which is like a good score for them, and then this algorithm comes back with that score, then we want to negate that in order to kind of illustrate that switching of turns from one player to the other. So then we call this method again recursively. This is again very, very similar to what we did here, where we called find move min max. The difference in here is we were switching the signs with this variable. From max, we called min with false. From min, we called max with false. But we're still going to pass in game state, next moves, depth -1. game state, next moves, depth -1. So same exact idea. And now we're going to pass in negative turn multiplier. So this is going to make it so that the score for black or white is always going to be positive. Basically, we're always finding a maximum score based on whose turn it is and then trying to maximize that. So we need a negative here, and we need this negative. If you forget this, your algorithm will not work. So this is really important that we have this little negative sign here. Then we can just check to see if the score is greater than the max score. Max score equals score. Another way we can do this, I haven't done this yet, but Python has a built-in max function. So instead of writing this, since we're seeing if score will be the max of score and max score, we can actually just say score equals max of score and max score. This is another way of writing that instead of that if statement. So it'll find the max of those two, essentially doing the same thing. The tricky part about this is this doesn't actually tell us if we found a new max. So the reason why I haven't been using that is because I actually do want to do something else inside of this, which is check if our depth is at our max depth, which, what variable do we use for that? We just use depth for that. So if we're at our max depth, then I want to set next move equal to that move. So I can't actually use the max function here because of this if statement here. I only want to set the next move to be move if it was a maximum score move. So it makes just more sense to just do it this way. So if you compare these two side by side, right, like this part here compared to this part here, it's you notice it's almost identical. The only difference is that little negative sign here, and that last parameter, instead of being a Boolean, is going to be -1 or 1, which is going to impact our base case. And so now this does the exact same thing as MinMax. It's just shorter to write, and that's our Nega Max algorithm implemented. So we can now, I'm going to modify, just minimize that method. We can modify this here so that instead of finding move MinMax, we find move Nega Max. And now we have to pass it, instead of a Boolean value here, we need to pass it 1 or -1. So we're going to pass it 1 if it's white's turn to move. So 1 if game state white to move, else -1 is the way we can do that operator there. So that'll pass 1 to it or -1 depending on who's calling it. And maybe I should, let's keep both in here just in case you wanted to go back to the MinMax. Oops. Okay. So we'll leave that one in there like that, and then we'll put our new one here. And I'm going to rename this from find best move MinMax to just find best move, since it's now going to call a different algorithm. And once we implement alpha beta, we'll change this to call alpha beta. Just kind of trying to do this one by one. We're making improvements as we go. So let's modify our main to find best move instead of find best move MinMax. Let's see, we have player 1, player 2. We'll test it, make sure we didn't make any errors in our code. So we'll run our main. Okay, so it's white's turn to move. I'm only going at depth 2, I believe, right now, depth 2. And so it will make moves relatively quickly. Notice it didn't take the pawn because it saw the fact that my queen could have captured it, so it didn't see that as a winning move. The issue is, again, we're not going to see any improvements in speed because now I'm attacking that pawn, so let's see what it does. Okay, it puts me in check. That's good. I'm going to go ahead and block the check with an attack on the queen. And so now it has to choose between these two. So maybe moving the queen in a way that, I guess I thought it would protect this piece, but I guess it's only thinking 2 moves ahead, so it didn't see that. Oh, no, I missed it. Oh, I just got owned. Okay. It did see that. Cool. All right, cool. It didn't lose the pawn because it was able to capture that one. All right. Let's see what it does here. Okay, just backing the queen out. Again, it's if I move here, it should attack this piece and take this piece. So let's see that it finds that move. And there it goes. It puts me in check. And if I move the king, it should attack my rook and grab that piece. And it could have grabbed either piece. It could have grabbed the bishop as well. But the rook was more valuable. All right, so we see it acting according to that. Again, this is only with depth 2, so it's not bad. The problem is, if I load this up to like depth 3, you'll even start to see it slows down dramatically. Like even this first move, it's loading in. Because it's actually creating all the moves for the first 4 moves of chess and evaluating those. And even though we didn't actually change our algorithm at all, the problem with this is that there's no real benefit to moving any pawn over the other one according to our algorithm. So even though it looks 3 moves in advance, it doesn't see any benefit to moving one piece over the other. So it does have to evaluate every single position. It's not finding any good moves anyway. So once we implement alpha beta pruning, we're not really going to see an improvement. And this, again, until we fix our score method, we're not going to see an improvement. So I want you guys to be aware of that. So I'm going to switch this back to 2, just so it doesn't take forever to run. And we'll now implement alpha beta pruning for the Nega Max. Okay. So I'm gonna copy this method to start, because I want you guys to have this so you can see the build up of it. But I'm gonna copy this and just paste it a second time. So we have this method twice, and I'm gonna say find move Nega Max alpha beta, because this will include alpha beta pruning with it. Okay, now the idea behind alpha beta pruning, you can get into a lot of theory. If you just search on the Wikipedia, I know has a decent explanation that is kind of layman's terms. The idea being, as we're going through our game tree and we're seeing all the different states of the boards, at some point we're going to get to a board where when we look at that board, down the road, we already found one move that benefits our opponent a lot. And so there's no point in checking other moves from that state, because the opponent already has a really good move. And so we're not even going to want to get to this state because this opponent's move is so good. So we can eliminate checking all of those various states. So one example of that is if the computer were to move the queen into a position that it would be able to get taken without being taken back. So basically trading your queen for nothing. Your opponent's not going to ignore that move if they're a good opponent. They're going to just take your queen. So there's no point in looking down at further moves beyond your opponent taking your queen, because they're just going to do that move every time. So why waste time evaluating positions that we won't actually get to. Assume your opponent's going to make your best move, make their best move, and that's what alpha beta pruning does for us. So same idea that we start with here. The difference here is we're going to have to add in a couple extra parameters. So we have two extra parameters that are alpha and beta. Alpha is sort of like our upper bound, and beta is our lower bound. And these are basically our values for our maximum possible and minimum possible scores overall. And so we're going to find, like, as we implement this, we're going to say if the max score is like already greater than alpha, that becomes our new alpha value. And if at any point alpha becomes greater than or equal to beta, then we break out of that tree, because that means like we found a maximum, we found a score basically that is better than any possible state that we could get from that position. Let me pull up a diagram to maybe better explain this. So here I have just like the picture I pulled up from Wikipedia that you can take a look at. But the idea being, so here's like our game state tree or a sample one. So we want to try, like, if it's our turn, we want to try to maximize our score. So if we go to each of these, maybe these are our three possible moves. And then from here, we have two possible moves, 2, 3, and so on. If we're evaluating from left to right, which is the case of we're basically exploring this move first and then exploring all the possible moves for that and all the possible moves. Basically, we get down to here and we find 5, and then we explore this tree and find 6. And so the goal of the algorithm would be to minimize here. So the minimum of these two scores would be 5. So we take 5, and that would be our current worst possible score. And then as we're evaluating these ones, we get 7, and then we see 4, and so 4 is less than 7. But 4 is also already less than 5, which means there's no point in evaluating this square. It doesn't matter what score was in this. We're already at a possible score of 4. That's like the lowest one to minimize. And since 4 is already less than 5, which we were trying to maximize, there's no possible value. It doesn't matter if this is like 1 or negative 1,000. Like, the thing is, this branch will never be evaluated, never meaningful, because if our opponent could get there, they would pick that. And so we will not make that move. We'll set it into this branch. We'll try to maximize our score. So that's the idea behind this. So we can prune off some of the branches. This is the most important one. So when we get to the end, we start to prune off a lot. So let's say we evaluate this. The minimum one we found in this was 3. The minimum in this we found was 6. Then as I get here, if I evaluate one branch and I find that that's 5, since we already have a 6 here and that 5 is less than the 6, then I don't even need to evaluate any of these moves, because there's nothing that I will find that is gonna that our opponent would choose. It doesn't matter the fact that this score is like an 8 and that would be really good for us, because our opponent would always put us in the state of 5. And since we already have a move that puts us in the state of 6, then like we would just choose that one. So that's kind of like how this algorithm works. And so we have these two like sort of variables that we're passing through the parameter, alpha and beta, which are keeping track of basically our minimum so far and our maximum so far. All right, so that's the idea. So let me get my code back up here. All right. So how do we implement this? That's what the alpha beta are for. So here we're going to modify our scoreboard to be the same in terms of just game state, right? We're not going to do anything fancy with that. That's going to be exactly the same. I am going to add in, I didn't add this in the move Nega Max. You could add this in if you wanted to. So we don't randomize. I think I shuffle the initial moves, which maybe is fine. So maybe we don't need to do that. Sorry, lost my place for a second. Okay, so like here, like a way to make alpha beta pruning more efficient is by move ordering. So we want it to evaluate the best moves first, because then we're going to find like scores that are better, and we won't look at branches that are worse. We won't have to look at as many branches that are worse. The idea behind move ordering is maybe you would evaluate all the moves that put your opponent in check first, because those are like forcing moves and they tend to have better scores. Or you might evaluate captures, because captures will sometimes give you better scores if it goes right for you. So we would implement this later if we want to do move ordering to make our algorithm a little bit more efficient. So that can also be a thing that we would add in later. We still start with our max score being negative checkmate, and we still follow the same idea: make move, get the next moves, and then here the difference is we're gonna still have negative find move, but we'll say Nega Max alpha beta. So we'll call our recursive one, and we'll have to add in our parameters. Now, we basically switch the values of alpha and beta each frame through. So we take our beta value, and that becomes the negative beta becomes our new maximum, our new alpha, and our negative alpha becomes our new minimum, because for our opponent everything is reversed. So this is basically our max, that becomes our opponent's new min, and this is our min, and that becomes our opponent's new max. And so this is where those max and mins are being passed level by level through that tree. Everything else is the same. The only difference now is the actual pruning that happens after we undo the move. We want to make sure we undo the move. Here we're going to check to see if our new max score is greater than alpha. So this is where the pruning happens. Then we will set alpha equal to our max score. That becomes our new best thus far. And so we can stop looking if we find a score that's less than that. And so the break case is whenever alpha is greater than or equal to beta. This is when we stop looking. And we break out of all the rest of the moves. We don't need to evaluate the rest of the moves for that tree, because we've already found the fact that this score is basically impossible to beat. And so there's no point in, or not impossible to beat, but it's worse and or better, depending on which perspective you're looking at, than some other move that we could have made in another branch. And so we will not make this move. So this is the implementation of this algorithm. It ends up being quite simple to implement. We only had to add in like a couple variables here, a couple variables here, and then a couple statements here from our Nega Max. But it ends up making it a lot more efficient, assuming our scoring algorithm is better, which it's not at this point. All right. So now when we're calling it, we call find move Nega Max alpha beta, and we keep everything the same, but we have to pass in alpha, which is negative checkmate, and beta, which is checkmate. Again, we're starting alpha. Alpha is like our current max, so we start that at the lowest possible score, and beta is our current min, so we start that at the highest possible score. And then we're as we find new mins and new maxes, we're slowly bringing those toward each other. And once they cross, that's when we know, okay, we've now found our cutoff point, if you will. So this algorithm is complicated. I didn't really go into an in-depth analysis of it or explanation of it. I tried to give you guys a brief explanation of it, but feel free to look into it a little bit more. There's plenty of like lectures and reading material on it. But I just wanted to focus on the implementation of it and give you like a little bit of understanding on it. Okay. Now, theoretically, we should see an improvement in our runtime because we're implementing this. But again, like we're going to see, this is still depth 2. It's still going to be relatively slow, I think. All right, it's not too bad. Looks like actually it's going a little bit faster, maybe. But again, this is depth 2. So let's see if we can notice any improvement with depth 3. I think that was a little bit faster, just from that first move, right? All right, I think, let's see if it finds that move right away. It also depends on the move order, right? If it looked at this bishop capture move right away, it would have been able to evaluate a lot less branches. But since our move ordering is always pawn moves first, it doesn't find them as quickly. But we can already notice it's definitely faster. It's definitely finding these moves a little bit faster than it was before at depth 3, comparatively to, let's go and switch this back. So our find best move, where am I at here? Ooh, I hope it's doing the right one. I have 2 methods called find best move now. Maybe that's, this one was only going through game state 2. Maybe that's why I actually saw it going faster. Let us, I'm going to comment this one out. I don't think it should have been that fast. Maybe it was. Maybe it's because I made that error there. So yeah, this was the algorithm we did a couple videos ago where it was basically the MinMax but without recursion. So this is MinMax without recursion. Maybe I'll just rename this one from find best move to find best move MinMax no recursion. So that was like the first thing we did, and then we did MinMax. Then we did, in this video, we did Nega Max and Nega Max Alpha Beta. So that's the one we're trying to call here with a depth of 3. So we'll see if that. Okay. So yeah, it did. It still is going a little bit faster. I think it was calling the right one. I think my guess is in Python, if you have 2 methods named the same thing, the second method is what takes precedence. Like if you named a variable, if you set x equal to 3 and then later set x equal to 5, x would have the value of 5. Okay. So not too bad. Definitely a little bit faster. You can see though, if you still go up to like depth 4, it is going to take a long time to load this in. Like first move, let's see. And especially as the board opens up and more moves become possible, it takes longer and longer. And once we implement our positional play, so we score the board based more on position, it should be able to cut a lot of these moves order. And we'll actually be able to evaluate to see how many moves it's evaluating with and without alpha beta pruning from a given position. So you can see it's taking forever. It's still thinking. And it's moved 2. So it did finally make a move, moved a pawn that could protect. That's a pretty good move. But it's taken a while to think. So in the next video, I'm going to go through how to make our scoring algorithm a little bit better, because there's really not much more we can do with the alpha beta pruning until we make our scoring better. Move ordering won't even really matter since all the boards are evaluating the same score. But it is a little bit faster. One thing you could check is, so maybe we'll do this in the next video, or maybe in a video later, just to see how many it's actually cutting off. We could evaluate, or we could have like a counter that goes through, and each time the method is called, we increment that counter by 1. And then in here, so we would have some counter. I can just do it right now, actually. So counter. So before we call the method, we would set counter to 0. And then at the end, we would just print the counter. So after we find a move. And this counter is basically how many times this method is called, which is, in other words, how many positions this state is running in. And just to show you the difference, I'll show you the difference between these two. So we'll do MinMax versus Nega Max. So let's have global counter here. And we'll just say each time it's called, we'll just increment counter by 1. And that's it. And then same thing with Nega Max. So we'll also put it into there. And this should tell us like some efficiency in terms of what we want. So we'll go depth 2 on the first move. And I don't actually think we'll see a difference with depth 2. So here, let's see. It evaluated 60 moves, and I don't think it pruned any. And then here, oh, it evaluated 0. Did I not put in the right one? Oh, yeah, my bad. That's the min-max one. Let's find move Nega Max. Valid moves, depth, and then we don't need alpha and beta. We just need this. All right, now we'll see how many times it counts. I think it'll also be 60. Oh, that's surprising, actually. Huh. All right, so the difference between Nega Max and alpha beta at depth 2 was actually quite a lot. Let's see what happens with depth 3. So this is without alpha beta pruning, depth 3. Still running through moves. It looked at 9,323 board states. 9,323 on move 0 at depth 3. And now if we look at our other algorithm with alpha beta pruning, let's see how that number changes. 9,323 down to 584. So that's a huge difference, right? That's like 10,000 down to 500. That's like 20 times, 20-fold. So you can see, yeah, even with a very, very shoddy scoring algorithm, we still see the pruning happen. I'm sort of skeptical of that. I'm wondering if I made a bug in this, which maybe I'll find later on. I don't think so. I as this is the first time I'm implementing on this, I think this is fine. I think this is implemented correctly. I don't think I'm made any typos or anything. Yeah. I mean, we'll see. If it doesn't work as we start to implement scoring and it starts to make stupid moves, then we'll take a look back at it. But I think it's good for now. So we can see the improvement there is actually pretty good overall. All right. So that's going to be it for this video. I'm at 40 minutes now, so I'm going to go ahead and wrap it up. But in the next video, what I'm hoping to do, and I haven't implemented this yet myself, so this might take a little bit of time for me to get the next one out. But my idea for making the scoring algorithm a little bit better is to sort of come up with in our engine class, I think the most efficient way to do this is rather than like looking through all the moves again and like finding which ones are, I'm going to evaluate them in terms of protection moves, threaten moves, and squares can move to, like squares a piece can move to. And I'll sort of keep track of 3 lists of these scores. So this will be a 2-dimensional array for all the squares each piece protects. This will be a 2-dimensional array for all the pieces that one piece threatens or attacks. So if like, let's say a knight, if it can't move to a square because its own piece is there, then that would be a protect move. So we don't want to just look at like, oh, if a knight can move 8 positions, then it's better than a knight that can only move to 3. Because if a knight can only move to 3, but can also protect 2 squares, then, that's better. So what I'm going to do is, as the engine is generating the moves, I'm also going to update these 3 arrays. So this is going to make our engine move algorithm, like get valid moves, a little bit more expensive, but hopefully not that much more expensive, because all we're going to be doing is just iterating values in a 2-dimensional array. We already have the row and the column that we're iterating. And so this should be not too bad to implement. We might have to keep track of them in like a log as well. So like if during an undo move, it goes back to its previous state. So again, I haven't implemented this yet. This might take me a little bit of time to get. If you wanted to try and implement this yourself, that's the idea. I think it will work pretty effectively. And then we'll be able to increase our depth, because in our pruning, because instead of looking at 584 moves, we'll only have to look at like 20 or 30, because we'll find that certain positions are just positionally better than other ones. So, all right, that's the idea. Thanks for watching. If you have any questions, you can leave them in the comments. I try to answer some of those occasionally. I'm sorry if I don't get to you. I do this as my job as well. I'm a teacher as well. So like a lot of my day is spent debugging code, and sometimes I just don't feel like debugging code. So, but I'll try to answer questions when I see them. But thanks for tuning in. Until next time, I'll see you.